let's talk a bit more about exactly what polarity means. Okay, and so when we talk about polarities of bonds, there's really different kinds of covalent bonds. You have nonpolar bonds where we think of the electrons being shared pretty equally, and then you have polar bonds where the electrons are being shared unequally. Whether it's polar or nonpolar, it can be thought of as being directly related to what the difference is in electronegativities between the different atoms in the bonds. Okay, and so the more difference there is in the electronegativities, the more polar the bonds get. So here are some rough guidelines. There's always exceptions, and it's really more of a continuum anyway, but if you look at the electronegativities of the two atoms in your bond and you subtract them, and it's really relatively small, maybe between 0 and 0.6, this is considered a nonpolar covalent bond. But if you look at the difference in electronegativity, it's a little bit bigger, maybe between 0.6 and 1.6, that's considered a polar covalent bond. And if it's greater than 1.6, then you aren't even really covalent. One of them completely lost the electrons, and the other completely gained the electrons, and it's more of an ionic bond. Along these lines, you can also talk about partial charges. Okay, and so if something is ionic, you have full-fledged positive or negative charges because something gained electrons to be negative or something lost electrons to be positive. But in these covalent bonds, you have partial charges, which are like small or slight charges in an atom in a bond. They're not quite ionic, but they have like a tendency to have a little bit more or less electron density around. Okay, and so the way to represent these partial charges is using things called dipole moments. Okay, and so we're going to use the Greek letter mu here for the dipole moment. Lowercase delta is the partial charge, and d is the distance between the charges. Okay, so if you have an atom here, another atom here, this would be the distance between them. Typical unit for a dipole moment is something called a debye. Okay, 1 debye is equal to 3.34 times 10 to the negative 30th coulomb meter. Here's the important thing as far as chemistry goes anyway. This dipole moment is a vector quantity, which means that it has a magnitude and a direction. So I'm going to depict these by using arrows or these kind of partial positive, partial negative symbols. Okay, so for example, if I look at HCl, the bond between hydrogen and chlorine is considered polar. The Cl is a lot more electronegative, wants to gain the electrons a lot more than the hydrogen does. Okay, so I can write this two ways. I could have delta plus, partial positive charge on the hydrogen, delta minus, partial negative charge on the chlorine because it's more electronegative, wants to gain those electrons. Or I can show with an arrow where the head of the arrow points in the direction of the Cl, and there's a little plus sign on the other side showing where things are going to be partially positive for the hydrogen. Okay, so this is partial positive, this side is partial negative. Okay. Here's where it gets a little tricky. Okay. What I just showed you would be the dipole moment for a bond, or the polarity of a bond. But when you have molecules, you can have lots of bonds in them. And so what I have to do to figure out whether the molecule as a whole is polar or nonpolar is look up what the individual dipole moments are going to be for each of the little bonds and then add them up. Okay, and so that's what this little summation means. Okay, add up all the dipole moments for the bonds to get the total dipole moment for the molecule. Because they're vectors and they have directions, it's possible that the overall dipole moment for the molecule is going to be 0, even if the individual dipole moments for all of the bonds are non-zero, okay, because of things that are symmetrical. For example, if I have one bond going that way and one bond going that way, and they cancel each other out, then there's no net dipole moment. And so even if the bonds themselves are polar, I could have a molecule that is nonpolar. Okay, so rather than using my hands and doing this, let me give you a specific example. Let's look at two different molecules, NOF and NO2F, and compare them. Okay, so first let's look at NOF. First, I have to draw the Lewis structure for this. So to get the total number of valence electrons, I have 5 from nitrogen, 6 from oxygen, 7 from fluorine. 5 plus 6 plus 7 is 18. Follow the rules for Lewis dot structures, and I come up with the following picture. Okay, so the nitrogen in the middle here is considered to be a bent geometry or angular because it has 1 lone pair up here and 2 bonded pairs. Remember, as far as VSEPR goes, single bonds, double bonds, triple bonds all count as one object. Okay, and so this would have 2 bonded pairs, 1 non-bonded pair. So very similar to a trigonoplanar geometry. So the angle here would be a little bit less than 120 degrees. So now let's figure out what the dipole moments are going to look like. Okay. Let's look up the electronegativities for these different atoms. Fluorine is the most electronegative element in the periodic table. That's given a value of 4.0. Oxygen is 3.5. Nitrogen is 3.0. So if I subtract the electronegativities between, for example, N and F, that gives me a pretty polar bond, right? Electronegativity difference is about 1. And the NO bond has a difference of 0.5. 0.5 is pretty close to that 0.6 cutoff. So that's kind of the border of polar and nonpolar. Okay, and so I can draw 2 little arrows, right? Dipole moments, starting at the nitrogen and going down, in this case, to the fluorine, which is more electronegative on the right. And this one is going down to the more electronegative element, oxygen, on the left. Point is that if I have one arrow going down and to the right and the other arrow going down to the left, net, kind of what I have is one big old arrow going down because the left and the right more or less cancel out, but the parts that are going down reinforce each other. So this is going to give me a net dipole going down. That's going to be pretty substantial. And if I actually measure this experimentally, it's about 1.81 dBi. Okay, so let's compare that to NO2F. Do the same kind of thing. Count number of valence electrons, draw the Lewis structure, figure out the shapes. Okay, so now I have something that looks like this. So now as far as the geometry goes, this should be trigonoplanar because I have 3 bonded pairs and no lone pairs. So the angles here are going to be about 120 degrees. Notice that there's actually resonance between 2 structures. The bond angles here are only very slightly different from the bond angles that I had in NOF. So if I compare dipole moments, the atoms are the same, so the electronegativities are the same. So I still have what I had before with one dipole moment going down like this and one dipole moment going down into the left like that. But now I have a new one. Okay, I'll draw it in blue, going up between the N and the O. So the point is that now there's going to be some cancellation because before I had this net dipole going down, and now I have this blue one that's going up. And the up and the down cancel out to some extent. So this is going to be less polar than the previous molecule, okay, less of a net dipole moment. And if I actually measure this dipole moment experimentally, it's about 0.47 dBi.